Adventure time?
Adventure time. Go and grab your friends. No, I never heard it. All right. Oh, you see the little dude? I'll switch it over. Hold on. So 2, 3, number 60. Doot. All right. Which one? Oh, yeah. Okay, perfect. Okay. Yeah, that's the one I told you to ask me, right? Okay, good. You did 59 correctly. I remember that. And I kind of like the way you did it, but it sort of hid from you what was really happening. Let's look at 59 first, because 59 is a little bit easier than 60. Anybody else try 59 yet? Anybody else try this homework at all yet? Some of you guys? Okay. All right. All right. You're good. You're good. You're not behind your head. I really want this to make all the sense of the world. When x is 1, what happens to the bottom on 59? Yeah, the bottom goes to 0, correct? That would mean that the answer should be infinity for everything except if what happens to the top at the same time. I really want this to make all the sense in the world. If the top is anything except something, if the top was 1, if the limit of this was 1, right? Then this would be, the limit would be 1 over 0, which would be infinity. If the top was negative 12, negative infinity. So the answer would be some kind of infinity for everything except one thing. What would the top approach for this to have a chance to not be infinite? I really want to, and you're all like, I don't have a clue, man. This shit. 0. That would be what kind of a form? Indeterminate. That has a chance then. Now, why does that work? Every time we've done a limit and we had to like factor it and simplify, what always happened when we factored and simplified? The problem died, right? So both the top and the bottom went to 0 in this case because for the same reason. So it kind of like gets out the way. Does that make any sense to anybody? No. No, okay. I really, let me see. This is such a beautiful problem. It's so small and yet it has so much shit in it. Oh. Come here, you. All right. What are you? Oh, okay. All right. Holy shit. All right. Ah! There it is. Okay. So if the limit of something went to like 1 over 0, let's say it goes to 1 over 0, right? If that was true, that would mean this is infinite. Yes? Is that cool? So for example, what's the limit as x goes to 0 of 1 over x?
Yeah, sorry.
That's all right. That's all right. You guys, is that cool? Is that all right? In fact, if the top is anything at all except 0, the answer is going to be some kind of infinity. So if I had this, let's just make this a little more direct. If I had this, all right, now think about this. This is, I think, this might be all I say about any of this. What must be true at 0 for both of these for the answer to be anything other than infinity? If the top went to 1, the answer is infinity. Is everybody cool with what I just said?
Yes. No.
If the top goes to 1, isn't this 1 over 0?
Yes.
1 over 0 goes to infinity. Okay, so if the top went to 1, this answer would be infinity. If the top went to negative 12, this answer would be negative infinity.
What?
You lost me.
Now we okay, that one.
All right, let's do this again. What's this limit?
Negative.
That's what I just said, right? Isn't it?
I needed to write it down. I'm a visual.
But why?
You tell me.
That's a great
Well, let me be more careful here. This kind of depends on the side we're coming from, so let me just make this x squared for right now. It's more like the other problem that we're talking about, right? So why is this true? Because as x goes to 0, isn't this negative divided by smaller, smaller, smaller? Isn't that negative big, big, big?
Yes.
Okay, I like it. So again, for every input, it's negative divided by smaller, 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 right? Because I'm going towards 0. So the answer is going to be negative infinity. If I just do this, now the answer is positive infinity. Okay, now, this answer, the minute you see this answer, I think both of those are going to be easier. Definitely 59, 60 might be a little bit freaky yet, but what would this have to be? What's the simplest thing that could be so that this would cancel?
5x.
Yeah, 5x. 5x. Now, again, let me do one thing and then I'll come back to that. What would I do here again? What did we do here?
Cancel out.
Or take out an X, yeah.
Factored out the top. Right? Don't forget your limit, Jeff. Model good behavior. And of course, what happens? The problem cancels. The thing that makes both the top and bottom 0 cancels. And you're left with something that works at 1. Yes? So the only way the limit of a ratio can be something like if there's, all right, how do I say this? Generally but specific. This is neat. The only way the limit of something where the bottom's going to 0 is anything except infinity is if the top also goes to 0, because they might go to 0 for the same reason and they cancel just like that did. So if somebody tells me the limit is 5, then I know the problem has to cancel. If both the top and bottom go to 0, isn't there a problem for both? And very often, not always, the problem cancels. So here, what's the only way to make this, and I think this is sort of related to what you did, now that I think about it, doesn't f over x divided by x have to equal 5 basically? So then doesn't f of x equal 5x? Yes? Maybe? No? What?
Explain that again.
So what's got to be true about that ratio as the input goes to 0? Let me push this over. As x goes to 0, that ratio has to become 5, right? So just because I know that, this is not something I can do generally. But for this problem, they gave me what the limit is. That means at 0, this ratio must be 5. Therefore, this ratio must be 5, so that's got to be 5x.
Oh, I thought that was okay. Yeah, that makes sense.
So the answer to this question is, what the hell is f? Well, f 5x.
Okay, and then that 5x is assumed to go to 5. Because how does the 5x equal to 5?
Well, now put a 5x in here, what happens?
Oh, okay. All right, that makes sense.
And then it's 5, always. Yeah, okay, I like it.
Where did the 5 come from?
It was given to me.
Oh, okay.
Okay, just like in this problem here. Yes, you can actually do the exact same thing, which is basically what somebody over there did, yes. Now that should come straight off of what we just talked about. And then number 60 is just like one little step up from there. So I'm going to let you guys, it sounds like not a lot of you are there yet. So I'm just going to wait for more of you to try that out. Yes?
Oh, I have the answer.
Don't say it. Yeah. Everybody else is like, huh? Oh, shit. don't say it. All right. Anything else from homework? Yes?
Could you explain number 10, section 2.3?
Oh, beautiful. All right, good. I think I told somebody else to ask me this too. Oh, yeah, okay. All right. If I, now what's funny is in algebra class, the teacher is often a little less formal, but technically, this is not a true statement. Now real quick, does everybody see where that came from? How do you do that? What do you do to get that? What do you do? Factor that out, the x minus 2's cancel, I love it. What's the one time you can't divide is if the bottom is 0, right? When is the bottom 0 at x equal 2? So you technically have to say, next to this, x not equal to 2. Then it's a true statement. Now what's different with, this is completely fine. I don't have to say shit here. I don't have to say a damn word here. This is beautiful the way it is. Why? What's the difference?
Because we're given a limit.
Yes?
Because you mentioned that the limit came from, is there a sign?
Nope.
It's coming from 2, which means that it can't
There's
equal
one
2.
little thing, guys.
We were able to factor it out.
Say again?
When we factored it out, we canceled out the bottom.
The same thing happened there.
Yeah, just give us.
So why is that wrong and this is right? This inherently cannot let x go to 2. So that's right. Because what's the only, I'm sorry if I missed somebody say that. The only spot this has a problem is at 2, and limits don't let it get there. So that's why that's beautiful. But up here, technically, I have to write next to this, x not equal to 2. Here I don't have to because I know x never equals 2. It just gets really close from both sides. Is that, it's got to be cool because it just basically answers the whole damn thing for you. So. All right. Maybe. Okay. So when I teach algebra, I do try to make that point that there are spots where that division doesn't work. So if x could be 2, I can't do anything with this. I like it. Anything else? Yes? 62? Oh, yeah. Okay. Sorry. I love this shit. Oh, sorry. I would. So, give me an example where the limit of each of these functions exists, but the limit of the sum of those functions doesn't. Right? So just to make sure you understand what that's saying. Does everybody capture what this asks us? I need to find examples of f and g so that the limit of each separately exists. Like the limit of f could be 7 and the limit of g could be 2. But when I add these two together, the limit does not exist. I want to make sure you understand the problem. Everybody understand what you need to do for this problem?
No.
So, you need to come up with a function for f, so it could be x squared minus 7 or something, and a function for g, where each one separately exists at a, but if you add the functions together, that new function does not have a limit at a. Does that make sense? Oh, I'm sorry. Yeah. It does exactly the opposite. If I would just read better. So this one, that's actually easier to do. So show that this sum could exist even though neither one of these exists. I like it. Yeah. So the limit is x goes to a of f does not exist. The limit is x goes to a of g does not exist. But when you add them together, it does. It's pretty simple once you understand, especially if I could explain it better. So that was my mistake, sorry. I read this backwards. I want this limit to not exist. There we go. Neither this one nor that one exists. So I don't want this one to exist. I don't want that one to exist. But when I add them together, I want that to exist. There's a very, very, very simple answer for this. And I'm just going to let that sit. Somebody think they have the answer? Don't say it. Anybody do that problem yet? No? Okay, so I'm going to let you guys try that problem out. So for example, what's the limit as x goes to 0 of 1 over x? infinite, so it doesn't exist, right? We can just be more specific about how it doesn't exist. It goes to infinity, right? So that could be one of the functions. Now think of another function that also does not exist at 0, but when you add them together, the result is fine at 0. There's a very, very straightforward answer to this, probably. Yeah, I think I saw that. Slide into second is on. Somebody's giving me gang signs. It's like, I don't know what to do. Don't hurt me. All right. And again, if you don't quite understand that, it's not the end of the world. It's supposed to be freaky. It's a little above the norm. Okay, maybe. If I give you an example, I give you the answer, so I'm not going to. So too bad. All right, anything else besides that freaky ass problem? Yes?
I have a really simple question.
I love it.
It's kind of silly, but
Kick ass.
2.343. I got 4, but I don't know where the sign comes from.
All right, so watch. All right, let me see. What is this? 0.5. Oh, I see. Okay. Let me give you a simpler example of what the main idea is. Let me find some. Where did I put all my paper? There it is. Yeah, okay. Can somebody tell me, is that equal to this? Hell no, right? But what if I told you, what's x plus 6 if x is greater than negative 6? If x is greater than negative 6, what kind of number is in there? And why am I asking like that? Because when's the absolute value do something different if the inside is positive versus negative? It does different things. Yes? If the inside is positive, does it do anything? Doesn't do shit. If the inside's negative, what does it do? Changes the sign. How do you change the sign of something mathematically? You multiply it by -1. I love it. So in this case, would the absolute value do something to this number if x is bigger than -6? Why? What kind of number is this? Positive. Then I could say this. Is that cool? If I just have that, I can't say that. I don't know, because I don't know what kind of number that is. But if somebody tells me what kind of number that is, well, how are they going to tell me that? They're going to tell me what the inputs are allowed to be. Now I know I'm dealing with positive numbers. I could just take the absolute value off. What is x plus 6, absolute value, if, what am I going to say now? Oh, shit, okay, that. What does that equal? What did we just say? How do you change the sign of something? You multiply it by -1. So I'm going to take x plus 6, and I'm going to multiply it by -1, right? That's how I change the sign of something mathematically, is multiply it by -1. So if you have a limit at -6 on one side, you can rewrite this like this. On the other side, you can rewrite this like this. Does that help? Isn't that a problem in that isn't that a problem spot? Which one was it again? 43, yeah. What happens at 1/2? Can you guys see what happens at 1/2? It's 0 there. But I'm coming from below. Do you see that? So can't you just take a minute and think, does that mean it's a positive number? In which case I could just take the absolute value away? Or does that mean it's a negative number? In which case I change the signs. Does that make sense? Why am I able to do something with this absolute value? Because they're being more specific. Right? So if I'm coming at, in fact, what can you do? What's below 1/2? Give me a number that's less than 1/2. 0. I heard 0. Right? But that's 0 there, isn't it? So you want something less than have like 1/4. You don't want to go all the way to 0 because it's 0 at 0 also. I don't know if you guys are understanding. So maybe put a 1/4 in there. Or factor the damn thing. And then it's easier to see, is it positive or negative if I have inputs below 1/2. No?
Yeah.
Maybe? Right? Okay.
What do the vertical lines mean?
Oh, okay. That is just absolute value.
Okay.
Yeah. All right, I like it. This is going to kill me someday. All right. Now, okay. Let's get into section 2.5. So 2.4 is our favorite section so far. Yes?
Just to clarify, the test is chapter 1 and then 2.1 through 2.5? Or are we?
No. The quiz is 2.1 through 2.5.
Okay.
The test
Uh-huh.
is chapter 1 and 2.
Okay, so we're going to do.
Because we're still going to cover the rest of 2.
Okay.
Yeah. Yeah.
A question on that last problem. Like 2-second thing. I was
Where was it? I just went. Okay, here.
for the question, it's asking to find if the limit exists. Why do we have to plug in an extra number if all we have to do is find that at 0.5 it equals 0?
The top and bottom are 0 at 1/2,
Yeah.
right? If I don't know how to simplify this thing, the absolute values are sort of in my way. I really want this, because if you factor the bottom, don't you get a 2x minus 1 in there?
Yeah.
Isn't it inside of an absolute value?
Yeah.
So I can't just cancel the 2x minus 1s because one of them is inside of an absolute value. I need to know how to rewrite this problem without the absolute value. Let me give you a more specific example. What if I had this problem here? Let me say this. There we go. I can't just cancel the x minus 6s. I cannot. Because I don't have an x minus 6 on the bottom, do I? I have an absolute value of x minus 6. Do I have that same thing on the top? No. So of course I can't cancel that shit. If only I can kill those absolute values, I could do something. They're in the way. Well, what kind of number is this, considering what I'm allowing inputs? Right? If I go to 6 from the right, I think I heard it, this is going to be a positive number. How can I rewrite the bottom then? No, come on. This is a positive number. What's the absolute value do if it's positive already?
Doesn't do anything.
Doesn't do a damn thing, yes? So I can rewrite this as x minus 6, x minus 6. Then I could do what? So this is 1. Yes?
And that proves that the limit exists.
That would show the limit exists. Exactly.
Okay.
Yes. Yes.
Okay.
So if you factor out x squared on 42, would that be on the outside or inside of that absolute value?
Technically, it starts on the inside, but because x squared has to always be positive or 0, it could just take the absolute values off.
Okay.
Yes. I like it.
Could you just put in like 6.1 and then do it that way? Since you're coming from the right anyway?
That doesn't tell you if the limit exists at
Oh.
whatever the
that's-
value is. Yeah.
Okay.
Okay. All right. Okay. So let's do 2.5. I've sort of already prepped you for 2.5. So let's see if this goes a little bit. What am I writing on? Okay, good. A little bit quickly. So let me ask you, what should be not too evil of a question. I don't even care what, well, sure. No, Jeff. You gotta love that. Okay. So, become a thing. Okay. Wah-ha! Wee-hoo! Okay. This is such a weird, it looks like a football play or something. I don't know what this looks like. I always love this kind of thing. That's trying to be a 1 by the way. So there's kind of 3 points I highlighted here, right? At x equal -1, x equal 1, and x equals 2. Right? Which one of those are kind of a strange thing that you're like, why would you talk about it? There's no problem there. 2. At 2. There's no problem at 2, right? Okay, so bless you. Which one of these values do you think this function is continuous at?
The one with the arrow?
Oh, you mean this?
Yes.
Yes, it's continuous here. Why is it not continuous here at 1? Because if I'm driving a car and I see this giant crater, can I keep going? No. And somehow I do some weird shit, right? That crater must have been really weird because I come right here and then I go, pop! So can I continuously move through this point? No. So that's why it's discontinuous at 1. This is technically called a removable. How do you spell removable? Discontinuity. Why do we call it removable? Because it's sort of like there was a pothole and they could remove the problem if they filled the hole in, correct? What happened to the city when they came out to fill the pothole? They put the filling off the side of the street. And we're like,
This is very relatable.
huh? It's almost relatable. Thank God they're not that bad. They just don't fill them in unless somebody draws something specific on it. Right? So, I don't know if you guys know. No? Okay.
No idea.
No, I understand. So, if they would have filled this hole in, would the problem have been removed? Would it be continuous then if I filled that hole in instead of filling it up here?
Yeah.
Yes, that's why we call it a freaking removable discontinuity. The name makes sense for once. Good job, math people. Now, I think I've told you already what kind of discontinuity this is. It's not removable because I don't care what I fill in. That ain't nothing going to save this, right? Yeah, it's a jump discontinuity. And again, good job, math people. Not me. I can't even spell, so. Discontinuity, okay. So there's a jump discontinuity. There's a removable discontinuity. There's one more kind of discontinuity. It would be an infinite discontinuity. Your good old, you shall not pass, right? I got that shirt. It's a little evil to wear to class, but I will wear it sometimes. Just don't take it personal. It's Gandalf there with you shall not pass. Ah, shit. I also call this, it's a trap. Ah! All right. So this is another discontinuity because I cannot continuously move through the whole thing. Yes?
Is that what's happening at 3? Or where is it on the graph?
These are two separate graphs. Two separate graphs. Yeah. Sorry. Here. So those are your 3 main types of discontinuities. Jump, removable, infinite discontinuity. Let's formalize this a little bit. Now that we have examples of what discontinuities could look like, how do we define what continuous is? Why is this one not continuous? Can somebody tell me in terms that we've used in this class so far, why is it discontinuous at -1? They don't agree. What doesn't agree? Be specific.
The line of the point?
Hmm?
The -1 from the left side.
Oh, okay, there you go. Kick-ass. The limits don't agree. The limits don't agree. 11. So this limit, of course, is 1, and this limit looks to be 3. Yes? So the limits don't agree. Okay, so now think about this. In our definition, it better include the idea that the limits agree. To be continuous, the limits must agree. Not only that, we're going to have some more shit, right? Because don't the limits agree here?
Yes.
Yeah, they agree. Why is this discontinuous?
The point doesn't actual
You guys are so quiet. Or am I just going deaf? I don't know.
the point doesn't.
There it is. I kind of agree with you, but Yeah, the value of the function at the point does not agree. So you need all kinds of agreement to get a freaking pothole filled in. We all know. So let's formalize this. Here's the formal definition of continuity. Continuous at a point. F is continuous at a point A if three things. Well, let me say it real quick first, and then I'll explain the three things. I could just write this, and this has a lot of information going for it. If the limit agrees from both sides, can't I just say the limit equals number? Yes?
Yeah.
So that's what it says. Doesn't it say the limit as it goes to A equals number? So hidden in this is the idea that the limit agrees. The limit exists. What else did we say? The function value has to, well, we kind of skipped this over, has to agree, but in order to do that, the function value has to exist. It has to be defined, right? And that's also here, because I've written f of a, which is assuming it exists. So let's break this out. So this is the definition. Let me explain the three things that are hidden. The limit as x goes to a exists. F of a is defined. Holy macaronis. Okay, there it is. F of a is defined. The value of f of a agrees with the limit. Those three things are all captured by just writing this. I write this, that means the limit exists. I write that, that means that's defined at A. And I write this equals that, that means that they agree. Okay, that's pretty straightforward. I've sort of been priming you for this since we started talking about limits. All right. What do you think it means for a function to be continuous on an interval? So this is all about continuous at a point, right? Are there intervals this is continuous on? Hell yeah. Can somebody give me the first interval this is continuous on? Let me be more specific here. Can somebody give me the first interval that this function is continuous on? Well, how do you answer that? What's the first place it's discontinuous? -1. So where is it continuous?
-3 to 1.
Up to -1. Stop.
What?
Is it continuous right there? Yes. Is it continuous right there? Is it continuous forever?
Yes.
Yes. So from -infinity up to where's the first place it has a problem where it's discontinuous? -1.
Okay.
So to be continuous on an interval means you're continuous at every point in that interval. That makes sense? Hopefully. So the quickest way to find that out is just identify where the problems are, and the continuous intervals are everywhere else. Okay. Continuous on some interval C to D means f of x is continuous at all a element of CD. Oh, Jesus. We have to bring in legal speak. To be continuous on an interval CD, that means the function is continuous at all points A where A is in CD. Okay, I like it. So far this makes sense, hopefully.
Does that say all A, comma
Yeah, this is trying to be a comma.
Okay.
At all A, where A is an element of the interval.
Okay.
Yeah.
Is that epsilon?
Yeah, it was like,
Do you guys ever seen that symbol before?
other than
This
down
means
here,
is an element of. Oh yeah, that is basically epsilon, you're right. But when I put it next to a set, it's set notation, it just means is an element of.
So am I ready? Is that a symbol or a comma or like what did you write
This
out?
thing is trying to be a comma.
Okay.
Okay. All right. Love you guys. What time we got? Holy shit. Okay. Here's the beautiful thing. If f and g are continuous at A, right? If f and g are continuous at a point A. Let me be more explicit. X equals A. So if f and g are continuous at the input A, right? They both are continuous there. Then all of these combinations are also continuous. Gosh, how do you spell? Okay. So you got f plus g, f minus g, f times g, c times f divided by g. There's one little thing about that last one, so let's see what the hell does this mean. If I have a function that's continuous at A, and I have another function that's continuous at A, then their sum is still continuous at A. Their difference is still continuous at A. Their product is still continuous at A. And what's the one little thing? Oh, I'm sorry. Does anybody know what this means? This is the function times any constant. Right? So is x plus 1 continuous everywhere? For you, it'd be like, all right, is x plus 1 continuous everywhere? What do you guys think? Yes. So what if I do 2 times x plus 1? Would there be some reason for that to be discontinuous? No, of course not. So any constant multiple of a continuous function is also continuous. What's the one thing I have to be careful about if I have two functions that are continuous and I divide them? Yeah, so I have to throw out anywhere that g is 0. So next to this, I better put g not equal to 0. Now, we're to the point where we can handle if I don't put an x next to f. So we can talk about functions a little more quickly now. You understand that's f of x times g of x and all that kind of shit. We're just not going to write that all the time so we can talk more quickly about these ideas. Okay. I like it. Yes?
And that's talking about the product of f and g, right?
fg? Yes.
Okay.
Not the composition because there's no o in the middle. Is that what you're worried about?
Yeah, okay.
So this is f times g, yeah.
Okay.
I like it. Composition we got to be a little more careful about. Yeah. I like it. And here's something kind of nice. I think, let me point out where this is. There is a beautiful little collection. I'm just going to jump ahead a little bit. Of all the functions that we are going to just know are continuous on their domain. These functions, polynomials, you know already. Polynomials are the most beautiful, good old Loch Ness Monster functions, right? Okay. So they're kick-ass. Rational functions, do they have problems?
Yes.
Are there problems in their domain? So what do you mean when you said rational functions have problems?
That means the denominator can equal 0.
The denominator can't be 0. Wouldn't I throw those out of the domain?
Yes.
So the problem spots are not in the domain. So do you notice what this says? These functions are continuous at every number in their domain. Yes?
Why are logarithmic functions continuous?
Well, we know this already. We've drawn their graphs, haven't we? So they're definitely continuous at every number in the domain. Where do you think there's an issue?
0?
is that in its domain? Is 0 in the natural log's domain?
No.
No. So the only spot that could have a problem is not in its domain. So let me ask you this. Let's look at natural log. Yep. So what's the natural log look like? Draw it for me. No. I liked half of that. Yeah, it's that. Shoop. Doesn't have that other part.
Oh, I meant normal log. Okay.
You mean like 1 over x?
What?
Okay. Is this?
Yeah.
So 0 is the only spot where it would be discontinuous. You guys agree with me? But 0 is not in its domain. So is the natural log continuous at every number that is in its domain? Yes. So on one level, you realize that theorem works because it is throwing out all the problem spots. So kind of like you should go, well, yeah, you throw out the problem spots, it's going to be fine. So on one level, you're like, well, duh. If I just say it's on its domain, beautiful. Are there functions that have problems even at numbers in their domain? Yes, because that list is not representative of every kind of function. Believe it or not. Because there are some functions you don't know about yet. Believe it or not. I like it. But all of these functions are continuous at every number that is in their domain. Okay, I like it. So for example, I mean, the easiest example of something you've already seen that that's not true for is a piecewise function, right? Piecewise functions do this weird shit, right? That very first example, where'd you go, first example? There it is. Is -1 in this guy's domain? Totally. Is it continuous there? No. But why is that okay? Did the list say piecewise functions? Nope, the list did not say piecewise functions. So that is the simplest example of a function that is not necessarily continuous at every number in its domain. I really want you guys with me. Does that make any more sense?
100%.
100%?
Yeah, definitely.
Some of you guys, I'm looking in your eyes and it looks more like 22% maybe. Yes? Okay. We sort of should have a feel for this already. Because when you draw, remember drawing rational functions, you had to find the asymptotes? And then didn't you just fill it in? You just filled it in with no problem. Yeah! You didn't go, oh shit, is this good? Oh shit, is this? No. You kind of already knew. It's continuous, except for this weird ass asymptote, right? You do that. It's sort of automatic. You identify the problem spots, and then it's good everywhere else. Right? This, over here, it's like this. I like it. So we're just sort of formalizing that knowledge that you've already used before. Maybe. So, for example, where is this function continuous? Is it not composition? Is it a collection of continuous functions?
Yes.
Natural. Where'd you go? Logarithm. Inverse tangent. Inverse trig. Polynomial, right? So it's a combination of continuous functions. So how do I identify where it's discontinuous? I just have to find what?
0 over 0?
No,
The domain.
not necessarily. I just have to find the domain, right? This is guaranteed to be continuous everywhere on its domain. So where will it be discontinuous?
Not on it.
This one's kind of neat. See if you guys can understand this. Well, you can kind of read the answer, but if most of you guys focus on this, yes?
Yeah.
But doesn't this have a problem? What does this guy say? X has to be greater than 0. And then what does this guy say?
Greater than 1.
Okay.
Well, it says it can't be 1 or -1, right? So far, okay. Where's my paper? No, I need more paper. All right. Shoot. So this one says it can't be 1 or negative 1. Natural log says it's got to be greater than 0. I like it. What about inverse tangent? Does that have an issue?
I'll write that.
Yeah, inverse tangent is beautiful, isn't it? Do you guys remember? You take the base tangent that goes from negative pi over 2 to pi over 2, and then you just flip that. So its domain is all real numbers. Its range is what's limited. Do you guys remember
Yeah,
that?
Yeah.
okay. Yeah.
Okay. So it's like, whatever, fellas, I'm fine, right? So what if you put all that together, what do you get? It's got to be greater than 0, but then I have to stop at 1, and then I can pick back up at 1 to infinity. So it's already stuff you've done. It's kind of beautiful. If I just said find the domain of this, you've done that before. Right? Maybe not for, natural log of x plus inverse tangent x, right? But it's still finding the domain. And that directly lines up with continuity because each of those functions were known to be continuous. So any combination of them is also continuous, right? Okay, I like it. Maybe. So we basically just did... Yes, ma'am.
I don't see how you got that information from the equation.
All right. Look at natural log by itself. Right? What's true about natural log? What's got to be true about x for this to work? For natural log of x to work, x has to be what? Does it work for any input? Can I get an answer for any input? No. What kind of inputs can I not get answers for?
0,
Good, 0. And of course, all of the
negative,
negatives. So what's got to be true about x then? It's got to be
positive.
positive, greater than 0. Kick x. That's where this came from.
Okay.
And of course, the bottom, where'd it go? There it is. The bottom can't be 1 or negative 1. Negative 1 I already threw out, right? So I just have to stop at 1 and start over. So greater than 0, but it can't be 1 either. So it's combining those two restrictions.
Okay.
I like it. So on one level, this should be easier than you thought it might be because you've been doing this already, your whole math career. Okay. You just didn't know you were doing continuity. Let's see, what other freaky shit can we look at? Blah, blah, blah. Oh, let's do this. Oh yeah, the 120 chart, I like it. Oh, let's talk about compositional functions.
You move it up.
Oh, sorry. Thank you. So let me say a couple things, right? If f and g are continuous at, let me see, how do I want to say this? Let me try it. If f is continuous at b and g is continuous at a, and g of x, no, get out of there, g of x, g of a equals b. Okay, there's a lot of ifs. So if f is continuous at b and g is continuous at a and g of a equals b. Okay, whew. Because what do you want to do to evaluate this limit? Don't you just want to throw a in? But in order to be able to do that, I have to know that g is continuous at a. I have to know that g of a equals something. And I have to know that f is continuous at that number. So what? And if that's all true, then this equals f of b. Crazy. So I'm allowed, so that whole idea of inputting values, and this is what I kind of dislike about the way things are organized in calculus, but it's kind of hard to ever get this perfect. But I can only input a value into a limit if that function is continuous at that value. And of course, that's why we simplify and kill, because then the result is continuous at the value we're trying to plug in. So that's why we kept, that's not just why we did that, that's another reason why we did that. Okay. So that's the composition deal. I like it. So let's look at another example, and then I think we'll call it a day. Oh, you know something? Yeah, let me give you this. I always forget what I have. Handout, especially when I made it last week. So this basically goes over what we talked about. Except for one thing. So there's a couple things on here, and then we'll finish this up next time. But let me look at a couple things real quick. And you're set here. All right. So obviously, you're going to see a lot of these in this section. A lot of graphs like this, a lot of piecewise stuff, because they're the ones that have the interesting discontinuities. What's happening at 3? Yeah, infinite on this side, right? And you can sort of call it a jump in a way, but not really. It like jumps forever down. Okay. The one thing I want you to, this is always a kind of a difficult problem here. This is where I want you to create a function that meets all of these requirements. So just very quickly, I think there's a few in the homework that are like this. Where do you think you would start? What do you think is the first thing you would throw down on the graph?
Points.
Hell yeah. I know if it's 0, 0, I mean, put a point, I mean, you start with the anchor points. You know those are true. So you throw those down. Where would the next place you go to?
The limits at numbers.
Yes. So, I mean, for example, what's going to happen at 5? And notice I don't say plus or minus, right? So can somebody show me in the air what has to happen at 5? You got to use both hands. Yes, there we go. Because it's got to be from both sides, because it doesn't specify. So it's got to be one of those, black hole singularity things. Oh shit, we're dead. Okay. These are interesting because from one side it's -1, from the other side it's 1. So let's do this. Let's focus at 0, and then I think I'll call it a day. So at 0, what's happening at 0? F of 0 is 0. Yay. That feels good. What's happening at 0? What's the function doing as I'm getting closer to 0 from above, from the right? It's going to -1. So what do I put at 0, -1? A circle. And from above, now you got to be careful because you got to keep an eye on the next number up that's got something weird happening. But I can do this, right? Like a little math sperm or something. But I know the next number I've got to be careful about is 5, right? But this definitely captures, it's approaching -1 from the right. Now what's happening from the left? What do I do to this? Yeah, another circle where? At 1, and then I have a little squiggly. I got to be a little more careful because I think it's -3 is where something else is happening. Right? So you can kind of take that into account. -3. Did I just circle over? No, okay. It's -3 period. So what's happening at -3? What should go at -3? The limit as I go to -3 is 2. So what should I put somewhere here? No. It's not infinite. What did we do right here? Oh, I see what you're saying. So an open circle. Okay. Open circle.
But it also says the minus. Yeah.
Say again, sorry?
Wouldn't it be close to that? Is that f of negative 3 is 2?
Yeah.
I know. But I'm just looking at this, right? But you're right. I could take this and put that there. The beautiful thing is, if you come back to that, you can just fill it in. No big deal. But just looking at the limit. And so what's got to happen between these two? In fact, where am I going to come off of? Am I going to come off of this? So now I got to come back to this. As I approach 0 from below, the outputs go to 1. So it's going to be wahaha. So this is where everybody's answer could be a little different, obviously. Right? Somebody could have went jihad, or somebody could have went woohoo, or somebody could just draw a straight line between them. Yes? No? Yes?
Oh, well, I guess my main question for the last limit, -3 to 2, wouldn't there be some form of like line that's traveling to from the left as well?
Yeah, totally. I haven't drawn it yet. Yeah.
Okay.
I like it. So now this would go from here, that way. Yes?
I don't understand why you connect those two.
So what's the limit as x goes to 0 from this side is 1, right? So my outputs should be approaching 1. As I come towards 0 from the left, my outputs should be going to 1.
Okay.
That's why I drew. You can just draw a straight line if you want to. Doesn't have to be some weird sort of thing. Now, the limit as x goes to -3 is 2. So from both sides, I got to be approaching that dot. The limit as x goes to -3, if it doesn't have a plus or minus, that means from both sides, it's got to be approaching that number. So both sides.
Okay.
Okay, I like it. Yeah. What's up?
I don't have a question.
Okay. All right. Yes.
So would we just put it like an asymptote as it approaches 5?
Yeah, at 5, this is the one we're just talking about. It's got to be that asymptote with that infinite well.
And it just does that from both sides.
Both sides, exactly. That's why it's like that. Because it's from above and below, because they don't have a specific negative or plus on it. Okay. I want to end there. So everybody knows what's happening in the near future. Cool. Quiz next Wednesday. Next Monday and Wednesday we're going to finish chapter 2, so that we're ready for the review day on next Friday.
Is it next Monday a holiday?
No, it's the Monday after. Yeah, next Monday's the 30th. Don't get too excited.
More time to study.
Yay! All right, let me know if you have any questions. Otherwise,
right?
you are free to go. Where are we looking at here?
The graph.
Oh, here.
Yeah.
Down. There's nothing after that. There. After 2 is -1. I like it. That matches up. Yeah, it looks good.
Perfect.
Make sure there's nothing else. Yeah, okay.
Limit's the only thing I'm good at.
Aw, come on. Oh, because inverse tangent is beautiful. Tangent is basic tangent goes like this. And it's got other. So if I invert that, it's going to be between those two, negative 5 or 2 and negative 5 or 2, forever. So it's kind of beautiful. It's continuous, everything. Yeah. Oh, be careful. So the limit as x approaches 2, which is here, is 0. Yeah. So it's got to be there. So like. So where's it got to come off? Yeah. It's got to come off of 2, right? So it would. There. Yeah. Because the limit as x goes to 0 or as x goes to 2 is, so that's both sides. So the little
Right.
circle you put on that, it's got to have it coming from both sides. Yeah. Okay. I like it. Thank you. Oh,
Thank you for your time. I have showed it
Yeah,
here.
let's see.
I have
And of course,
I gotta get it for this.
you
Like,
use it
when I
on
lay
that
down to
side,
this one and then I get up.
otherwise
I
this
just-
wouldn't be true. Where'd it go?
I think it's fine.
Because that's from
The
above
thing is,
angle.
I can move it though.
So on this side, there's nothing else going on.
What happened?
You do whatever you want to, as long as it does this.
Passengers
Yeah.
at the start of like warm-ups.
You
heard it? J-Lon came down and he went
Yeah,
hard
the
too,
only
so I was
place
like,
it can
okay,
be
he wasn't
discontinuous
hard. I felt that
is
just
-1 or 1.
sting. I was like,
Right? So let's see.
I was like, why are we doing this at the start, right?
But think about this. At -1, it's -1. Where does this pick up? What is this? I'm not allowed to put a -1 in. But where would I put the open circle?
So
Where do I get when I put a -1 in?
this open circle at 2.
Yeah.
Which one does that have a -1? So it would be right on top of that one. So that would not be discontinuous then, because it connects. It doesn't matter that it like does a hard turn or something. It just needs to be filled in. It just needs to, yeah. Okay. You're welcome.
I was wondering if I could just do my broad colors, so like work on basically showing my work.
To do what else?
Or just work on basically, a couple of just ideas, but definitely just working on
And
how to
to-
show my work.
What was the first thing you said?
Show my work. Or like just kind of.
You said
figuring
something
out
about
what's
office
the
hours?
minimum. Yeah.
Okay, so what about office hours?
Or yeah, just one, or yeah, I know when the times are, but I just need to, or I was going to have an appointment thing, so I just gotta.
No, no. In fact, the best way to do it is I'm in this room
So
from 8:15 to 9.
Okay, so I'll just come in.
Every
like on
Monday, Wednesday, Friday.
next Monday.
Yeah.
Yeah, yeah, yeah. Just come in early.
Alright, oh, cool. What are their documents?
Oh,
Building
probably
10.
right there, that building, or there's,
No, I looked in building 20 before class.
And there's nothing?
I don't think so. So I have to walk all the way to.
yeah, the
building 10.
administration building, yeah.
Alright, that's fine. Alright, thank you.
Sure.
Okay. I think I've made enough, all the corrections I've wanted to, so I should be at like 99 points.
Okay.
Okay, so yeah, that's it.
Yeah, okay.
That's how this grading works, right?
What's that?
That's how the grading works, right? I did I corrected.
You could
two.
get 5 points back max.
Oh, okay.
So anything 80 or above, you can get 5 points back max. You get below an 80, you can get a point for every 4 points you missed max.
Okay, I think I'm good.
Okay.
I would push
How would you? So how would I finish
Oh, so since, let's look at 5. This says as x goes to 5, so it's got to be from below and from above. So on this side, there's nothing else about this side except as it goes to 5, it's got to go down infinitely.
Yeah.
So this side, you got a lot of, as long as it's coming down here, and there's an asymptote here, you're golden on that side. But if you only left it the way it is, it's not true, because this doesn't just say from below. It doesn't have a negative. Yeah, so it's got to be from both sides.
What about this? Because right here it says as x is getting closer to 0. but
Yeah,
here-
you currently got it going to -1. Now listen, you got it. Let me see. Oh,
And I know that that's right, that's right, that's right.
so at
I
at 2, it is -1, right?
Well, I know.
But what are the limits supposed to be approaching?
That was stupid, too. I fixed that, I fixed that.
So there's just
that.
there's just
So the line is about this one, and that's right.
Jump discontinuity.
So, I mean, even if we get one wrong.
So the function value could have nothing to do with the limit,
yeah.
of course, because the limit has no idea what's actually happening there.
I was gonna question about 4 and 8. And so I was finding it wrong because it didn't hide an extra parenthesis in there below the comma 2 and that, or
Well, there was a lot that didn't make sense. Here it says greater, right? It doesn't make sense. This doesn't make sense.
what would be the first step to do?
Okay, and so the whole inequality thing, why? What's the only thing that can't happen in a fraction? The bottom cannot equal 0. Not greater than 0, not less than 0. There's no inequality. So if you just say the bottom, 3x squared, blah, 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 not equal to 0 and solve it, you're done. Yeah, yeah, so that's the factoring step that I need to see a little more about, yeah.
I need to start using my test code.
Yeah.
Where do I get the test out?
Oh, yeah, yeah, you didn't get your quiz back?
Yeah.
What's your name? Alright, so what happened there is the original, and then a curve. And then you can make corrections.
Yeah, test corrections, I can bring them in on Monday.
Yeah, you have until the test. So you have until September 8th.
Yeah.
You can turn them in anytime before that, yeah? Sure.
For this graph, what if it takes as a whole?
Yeah, I like it.
Right.
Because the limits have to go to 0, but the function wants to be a -1. I like it.
So
That's good.
For my domain on this one, would the piece already be?
The only thing, the only input that does not have an output is there. Right? So I can go from -6 all the way up to 4, because everything in the middle has an output.
So I don't have to do all of this.
You don't have to stop somewhere, because you see how you included
Yeah.
that, so why would you even write this?
No.
So you just keep going, -6 up to 4, that's where you have to stop and start again.
Okay.
Yeah.
So then with the range, is that the same thing? Because since it's 3 different functions, would the range change relative?
No, so here's the middle. Now again, so the range is what do I get as outputs? Don't I get everything up to here as outputs?
Yeah.
Yeah.
Okay.
So see how I kind of focused on the one that's got the widest range?
Yeah.
So this is included, and it goes all the way up to there, that's included. It almost doesn't matter with these two, because that's just continuous.
So you
That's the
just-
highest, that's the lowest.
So you just always want to include the most, like the tallest graph.
Yeah,
So-
the only place that the range would have a problem is if, for example, there was something like this. The domain has a problem here, and so does the range.
Yeah.
Or it could be something like, this,
Yeah.
then the range has a problem. Now that's a really big problem, yeah. Good lord, there we go, that's good. So here, the domain is everything, but the range starts here with a parenthesis.
So if that's the case with how you told me just the one thing, would that just be the same thing with the decreasing and just only focus on?
The only thing you did with the decreasing was you can't include the endpoints because I don't know. Yeah, and I think this one is the one I definitely needed a better approximation for. Yeah. That was really the reason you lost is right there. Just a better approximation.
Alright, thank you.
Sure. Yeah.
Number 36, which is a dispute there, it says like.
Yeah, I'm surprised nobody asked me about it.
What are we
So,
technically supposed to do?
all right, look at all that shit. Which one of those do you know the boundary of a ring with the outputs?
Is it the sign?
Okay, so what's the sign live? What sign of what? It doesn't really matter, but was it pi over x or something?
Yeah, pi over x.
What's that always got to be between?
-1.
Now, can you multiply all of these by the piece that you're missing to create the function?
Yes.
Then you could do the limit of this and the limit of that, and they're both the same number. That's got to be that number also. That's the squeeze.
So like that's what I'm so when I stop.
Yeah.
That's the
Now, the answer is, what's the limit of this as x goes to 0?
So plug it in.
Yeah, yeah.
Okay.
So that's a nice function. There's no problem. There's no weirdness. That's just 0, right? And the same thing for that. So the limit of this has to be 0 because it gets squeezed. If those two both go to 0, and this function's always between, oh shit, it's got to go to 0. Yeah. So that's kind of like we take the weird shit. This is weird.
Yeah.
But we know it's got to be there. Then we multiply by the rest to make the function I really am curious. And then I could do the outsides, and then the weird inside just gets squeezed. I never have to evaluate this directly. That's the beauty of the squeeze theorem.
So technically the answer is the limit of 0 with this.
Is 0 because the limits of both sides are 0, so it squeezes your actual function to 0. Yeah.
Got it, thank you.
I like it. Oh, am I still recording? Yeah.